In the last video we talked about sample preparation, the work that happens before a sample reaches the instrument. Today we're going to cover the mathematical foundation that sits on the other side of the measurement: units, concentration, and calibration. These are the tools that take a raw instrument signal and turn it into a number that actually means something. This video is more quantitative than the previous two. If some of the math feels unfamiliar, don't worry, we'll build it up step by step, and the concepts are more intuitive than they might first appear. Let's start with concentration, because it's the single most important quantity in analytical chemistry. Concentration expresses how much of a substance is present in a given amount of another substance, usually a solvent or a mixture. When we say a sample contains a certain amount of lead, or glucose, or pesticide, we almost always mean a certain amount per unit volume, or per unit mass, of the sample. Concentration is the answer to the quantitative question, not just how much, in an absolute sense, but how much relative to something else. There are several ways to express concentration, and you'll encounter all of them depending on the context and the field you're working in. The first is molarity, expressed in units of moles per liter, abbreviated as mole per liter or simply m. Molarity is the standard unit in chemistry labs and is fundamental to stoichiometry and reaction-based methods. If you have a 1 molar solution of sodium chloride, that means 1 mole of sodium chloride, about 58 grams, is dissolved in enough water to make 1 liter of solution. Molarity is precise and chemically meaningful, but it requires you to know the molecular weight of your analyte, and it isn't always practical in fields like environmental science or clinical chemistry, where you're dealing with complex mixtures and trace concentrations. That's where parts per notation comes in. You'll see this constantly in analytical chemistry, especially at trace levels. Parts per million, or ppm, means 1 unit of analyte for every 1 million units of sample. In a liquid or solid context, this is equivalent to 1 milligram per kilogram, or 1 milligram per liter, since 1 liter of water has a mass of approximately 1 kilogram. So if a water sample contains 5 ppm of a pesticide, that means 5 milligrams of that pesticide per liter of water. Parts per billion, or ppb, takes this a step further. 1 ppb is 1 microgram per liter, 1,000 times smaller than 1 ppm. Environmental and clinical analyses often work at ppb levels. Some techniques, particularly those coupled to mass spectrometry, can reliably detect at parts per trillion, ppt, which is 1 nanogram per liter. To keep these in perspective, 1 part per million is roughly equivalent to 1 second in 11.5 days. 1 part per billion is 1 second in 32 years. These are genuinely tiny amounts, and the fact that modern instruments can detect them reliably is one of the remarkable achievements of analytical chemistry. Parts per notation also applies to gases, where concentrations are often expressed as volume ratios, ppm by volume, or ppmv. You'll encounter this in air quality monitoring and industrial hygiene. Another common unit, particularly in clinical and pharmaceutical settings, is percent concentration. This comes in a few forms. Weight per volume percent, written as with V%, expresses grams of solute per 100 milliliters of solution. So a 5% with V solution of glucose contains 5 grams of glucose per 100 milliliters. Weight per weight percent, or with W%, expresses grams of solute per 100 grams of total solution. This is used when working with solids or when density matters. Volume per volume percent, or V%, is used when both components are liquids, the most familiar example being the alcohol content of beverages, expressed as a percentage of total volume. Knowing which percent unit is being used matters. A 5% with V solution and a 5% with W solution are not the same thing, and confusing them introduces error. Now, all of this is about expressing concentration once you know it. But how do you determine the concentration of an unknown sample from an instrument signal in the first place? That's where calibration comes in. Let me explain the underlying principle first. Most analytical instruments don't directly output a concentration. They output a signal, an electrical voltage, a peak area on a chromatogram, an absorbance value, a count rate. That signal is related to the concentration of the analyte, but the relationship has to be established before you can use it to determine unknowns. Establishing that relationship is calibration. The fundamental assumption behind calibration is that there is a predictable, consistent relationship between signal and concentration. In most cases, over a certain concentration range, that relationship is linear: double the concentration, double the signal. This is expressed mathematically as a straight line. Signal equals slope times concentration, plus an intercept. To build a calibration, you prepare a series of standards, solutions that contain known concentrations of the analyte. These are called calibration standards. You measure each standard with the instrument and record the signal. Then you plot signal on the vertical axis against concentration on the horizontal axis. If the relationship is linear, the data points fall along a straight line, and you fit that line mathematically using linear regression. The result is a calibration curve, or, when the relationship is linear, a calibration line. The equation of that line is your measurement model. When you then measure an unknown sample and get a signal, you plug that signal into the equation and solve for the concentration. This is the backbone of quantitative analytical chemistry. Every quantitative technique you encounter in this course uses this principle in some form. Let's talk about what makes a good calibration. First, your standards need to bracket the expected concentration of your unknown samples. If your samples are likely to contain analyte concentrations between 1 and 100 parts per billion, your calibration standards should span that range, not be clustered at one end, and not stop short of the other. Extrapolating beyond the calibrated range is unreliable and should be avoided. Second, you need enough points to define the line with confidence. A minimum of 5 to 7 calibration standards across the range is typical in most regulated methods. With fewer points, you can't reliably assess linearity, and your regression is more sensitive to the error in any single measurement. Third, your standards should be prepared in a matrix that matches your samples as closely as possible. If your samples are in an organic solvent, your standards should be 2. If your samples have gone through a particular extraction procedure, ideally your standards should as well. This minimizes the impact of matrix effects on the calibration. Fourth, the calibration should be performed on the same day as sample analysis, using the same instrument under the same conditions. Instruments drift over time, temperatures change, detectors age, columns degrade. A calibration from last week may not accurately reflect the instrument's current response. Now there's an important concept that sits alongside calibration: the linear dynamic range. Every instrument has a range of concentrations over which the signal responds linearly to concentration. Below the lower end of this range, the signal becomes too weak to distinguish from background noise. This is the detection limit. Above the upper end, the detector saturates, the signal no longer increases proportionally with concentration, and the calibration curve bends. Measuring outside the linear dynamic range produces unreliable results. The detection limit deserves a brief explanation because it comes up constantly in analytical chemistry. There are actually several different ways to define detection limits, but the most common are the limit of detection, or LOD, and the limit of quantitation, or LOQ. The limit of detection is the lowest concentration at which you can reliably distinguish the analyte signal from background noise. At the LOD, you can say the analyte is present, but you can't necessarily put a precise number on how much. The limit of quantitation is a higher concentration, typically 3 to 5 times the LOD, at which you can reliably quantify the analyte with acceptable precision and accuracy. Below the LOQ, you may detect the analyte, but your concentration measurement isn't reliable enough for reporting. These limits are not fixed properties of an instrument alone. They depend on the analyte, the matrix, the sample preparation, and the measurement conditions. Optimizing sample preparation to concentrate the analyte is one of the primary ways to push detection limits lower. Let me introduce one more concept that's critical for understanding calibration in practice: the difference between accuracy and precision. Accuracy refers to how close a measurement is to the true value. If a sample truly contains 10 ppm of a compound and your measurement gives 10.1 ppm, that's accurate. If it gives 15 ppm, that's inaccurate. Precision refers to how reproducible your measurements are, how close repeated measurements of the same sample are to each other, regardless of whether they're close to the true value. If you measure the same 10 ppm sample 5 times and get 9.8, 9.9, 9.8, 9.9, and 9.8, that's precise. But if the true value is 10, it's also slightly inaccurate. You can be precise without being accurate. You can be accurate on average without being precise. The goal is to be both. In the context of calibration, systematic errors, such as a contaminated standard, a matrix mismatch, or an instrument drift, tend to affect accuracy. Random errors, instrument noise, small variations in technique, affect precision. Understanding which type of error you're dealing with points you toward the right corrective action. There's one more tool worth introducing here: the internal standard. An internal standard is a compound that you add to every sample, every standard, and every blank at a known, fixed concentration before analysis. It goes through the entire analytical process alongside your analyte. After analysis, instead of using the raw signal of your analyte to calculate its concentration, you use the ratio of the analyte signal to the internal standard signal. Why does this help? Because if something varies between measurements, injection volume, instrument sensitivity, sample preparation recovery, it affects both the analyte and the internal standard equally. Those variations cancel out in the ratio, giving you a more accurate result. A good internal standard behaves as similarly as possible to the analyte, similar chemical properties, similar behavior during extraction and analysis, but produces a signal that can be distinguished from the analyte signal. In mass spectrometry, isotopically labeled versions of the analyte itself are often used as internal standards for exactly this reason. You'll see internal standards used throughout this course, particularly in gas chromatography. Let's bring this all together. Concentration is the fundamental quantity we're trying to measure, and it can be expressed in molar units, parts per notation, or percent depending on context and scale. Parts per million and parts per billion are the workhorses of trace analysis. Calibration is the process of establishing the relationship between instrument signal and analyte concentration, using a series of known standards to build a curve. That curve is the measurement model that converts signal to concentration for unknown samples. Good calibration requires standards that bracket your sample range, enough data points to establish linearity, matrix matching, and fresh calibration on the day of analysis. The linear dynamic range defines the concentration window in which your instrument responds reliably, bounded at the bottom by the limit of detection and at the top by detector saturation. Accuracy and precision are distinct qualities, and analytical methods need to be validated for both. And internal standards are a powerful tool for correcting for variability in the analytical process.